Hey guys, let's take a look at the second question on 2021 AP Chemistry. So the first question for 2A, the question is asking mass spectrum of the pure sample of silicon is shown below. So majority of them are silicon 28. There's some amount of 29 and 30, but a lot of them are 28. That's the most abundant isotope for silicon. And the question is asking how many protons, how many neutrons are in the nucleus of an atom with the most abundant silicon. So we're looking at silicon 28, 14 proton, 14 neutrons, a relatively simple point for this question. And second one represents, guys, question is asking, write the ground state electron configuration for silicon. So typically when they did not say write a full configuration. So when they say, you got to watch out for the term full configuration. So when they ask for full, you got to write 1s2, 2s2, 2p6, 3s2. You have to write all the way from the beginning from 1s2. But now, since they're asking just for the ground state configuration, you can write it as abbreviated version of this. Okay, so you bracket neon with the 3s2, 3p2. That's good enough of an answer to get a point for the second part. So in part B, question is asking, so there are two compounds that contain silicon, which is silicon SiO2 and what? SiH4. They're asking part B at 161 Kelvin, okay, SiH4 boils, but SiO2 remains solid. They're asking, using the principle of interparticle forces, explain why difference in the boiling point. So, boiling point has a direct correlation to what we consider as the vapor pressure of a substance and also the intermolecular force of a substance, okay? So, meaning, as we know, stronger the IMF, intermolecular forces, okay? The IMF is really strong, and regardless of what IMF it is, right? It could be hydrogen bonding, LDF, and such. Stronger the IMF, every molecule is holding onto each other with a greater force. What will happen is there'll be what? So which means it'll have a lower equilibrium vapor pressure because less of the particles turn into gases. If you have a lower vapor pressure, what happens? The result will be at a specific temperature value, it will have what? It will have higher boiling points. So this is what's going to happen. So stronger IMF, lower vapor pressure to result in high boiling points. So I'm sure you've seen a graph, right? This represents temperature. This represents the vapor pressure. So when a substance have a strong IMF, they have a lower vapor pressure for certain temperature values. So it'll be more like this. So compared to this, substance that has a higher vapor pressure will be like this. So this is one that has a lower, one that has what? A weaker IMF. This is the one that has a stronger IMF. Again, if you have stronger IMF, they have a lower vapor pressure. So in turn, if you look at this, right? So if the pressure of the outside is 1 atm, so if you look at this, then, okay, so when the vapor pressure becomes equal to the outside pressure, and this point here is what we call the boiling point. That's the definition. Okay, so now, as you can see, the one that has a stronger IMF has a higher boiling point. Okay, so it seems like this question is asking about the intermolecular forces because, as what the question states here, SiH4 remains, it boils, turns into a gas, but SiO2 doesn't, remains a solid. So it kind of gives you the understanding that, from the question perspective, that SiH4 has a weak IMF, SiO2, it has relatively strong force of attractions. But now, one thing that you have to understand is that SiO2, silicon dioxide, is one example College Board gives you a lot as what we call a network solid, such as diamond, right? So a carbon, which is a diamond, right? And silicon dioxide, these are both an example of a network solid. So what is network solid? Network solid, sometimes they give the terminology of network solid as what they call as a macromolecule, which is, it's a large molecule. So reason why they call that is what? Because every atom is bonded to the other atom with a covalent bond. So there's no IMF. So IMF doesn't really apply for these guys because all the atoms are bonded to the other atom with a covalent bond. And as we know, covalent bond is what we call intramolecular force of attraction, inside the molecule. So that covalent bond is much stronger than any IMF that's out there. So LDF, hydrogen bonding, is weaker than covalent bonding. So because every atom is bonded to the other atom with the covalent bonding, which is a stronger force, they're more likely not to turn into a gas that easily as what you see from the SiH4. So I'm going to answer this question. So so you should kind of mention that SiO2 is a network solid. Okay, network solid have a very high melting point and boiling point, which is the reason why they do not turn into a gas. And then you have to mention that the SiH4, that will be a non-polar, a covalent molecule. So when you guys draw SiH4, silicon in the middle, hydrogen surrounds it. So due to the symmetry of the molecule, this is a non-polar molecule. So non-polar molecules have LDF, London dispersion forces. And now LDF, the strength of LDF depends on the size of electronic cloud, which is the number of electrons based on Pallas boards. So, because this only has LDF compared to the network solid of SiO2, this one should have a weaker IMF, which means it should have what? Lower boiling point compared to the one that has a really strong force of attractions. So that's how I'll approach part B for number 2. And part C. Question is asking, write a balanced equation for the reaction for a silicon SiH4 decomposing to form a solid silicon and hydrogen gas. Let's write a balanced equation for this. So as how the question wants, so let's write SiH4. So turning into a silicon solid plus 2H2 gas. You gotta write the balanced equation for this. So I will probably put gas here because we discussed that this was most likely found as a gaseous form. And this is the balanced equation for part C. And part D, they gave them the absolute entropy value. So keep in mind, guys, entropy, absolute entropy for individual compound or substance are always positive, okay? Because as we know, based on the third law of thermodynamics, at 0 Kelvin, that's when you have perfect crystals with the 0 absolute entropy value. So when temperature goes up, entropy value should go up as well. And that's the reason why you should not have a negative absolute entropy values. So they provide the value for the H2SI silicon and also SiH4 as well. And part D is asking, explain why the absolute molar entropy of silicon solid is less than H2, which is a gas. So, as you guys all know, solids have the least entropy, and then it's liquids, and then it's a gas. So as you go from solid to liquid to a gas, the entropy, the absolute entropy value increases. Okay, so you probably have to mention about the phases, because silicon is in a solid phase, while H2 gas in a gaseous phase, and that's the reason why H2 gas have a greater absolute entropy compared to a silicon, which is a solid. That's something that's mentioned in part D for number 2. In part E, question is asking, calculate the value joules per mole times Kelvin for delta S at standard state for the reaction provided, which is the equation that we wrote here. So, I mean, as you can see, if you write a wrong equation, then potentially, you probably get the answer wrong for part E as well. So now, the equation for delta S at standard state. So this is delta, which is what? Keep in mind, guys, delta doesn't mean changes. Delta means what? In chemistry AP, final value minus initial value. So product minus the reactant. So, which is equal to what, guys? How do you get this? You have to add the entropy value for the reactant, for the product, minus the entropy value for the reactants. So delta S at standard state is equal to, so let's take a look at these guys, okay? So silicon is given as 18, okay? And now hydrogen is what? Is 131, so plus 131. But since there is a 2 here, which is a coefficient in front of the H2, which is 2, we gotta multiply this by 2. So you gotta add the entropy value for silicon and hydrogen gas, which are the products, minus the entropy value for SiH4, which will be minus 205. The answer will be 75 joules per mole per Kelvin. That'll be the answer, guys, for part E. This is part E, guys, for number 2. Okay. And the way that you have to calculate for delta S for the reaction is very similar to calculation for delta H of a reaction or delta G of a reaction if the absolute values are provided to you. Okay, like heat of formation for the individual elements and compounds, and also the delta G value of formation for the reactant and products. Then you can use the same equation, same logical equation to solve the question for delta S and delta H and delta G values as well. And part F, question is asking, the reaction is thermodynamically favorable for all temperatures. So terminology is saying, guys, I mean, thermodynamically favorable means what? It's a spontaneous reaction. It's a spontaneous reaction at all temperature. So, I mean, again, delta S is positive, right? Based on what we got in part E. So how do we know, guys, the reaction is thermodynamically favorable? What is the deciding factor is delta G. So the equation provides, guys, this is part F, right? So delta G is equal to delta H minus T times delta S. That's the equation that we talked about many times. So if you take a look at this, guys, so they're saying we know that delta S is positive, okay, which helps the delta G to be negative. So when delta G is negative, that's when we know that the reaction is spontaneous. And they also mentioned that the reaction is thermodynamically favorable at all temperature, which means, I mean, that they're kind of hinting that what this is also negative, which means it'll be thermodynamically favorable, it'll be spontaneous reaction almost at all temperature values. But the question is asking, explain why the reaction occurs only at a high temperature. What they're saying, what the question is saying is what? Although the reaction is spontaneous because it's hinting that delta H is negative, delta S is positive, the delta G being negative, which means the reaction must be spontaneous. But they're saying reaction is just not happening at all temperature values, but it only happens at high temperature. So there are a few questions that the College Board provided to where even though thermodynamically the reaction is favorable, but there are other portions that to look into, which is what we call the kinetic perspective of the reaction. In the kinetic perspective, okay, so yeah, we get it, okay, the reaction is going to happen, but again, delta G value is something we call a state function. They only look at initial and final value. So, and they don't which means the process doesn't matter. So delta G says, okay, so if the delta G is minus 100 kilojoules, the reaction is spontaneous, but it doesn't tell you how long it takes to get there. So the time it takes to get to the reaction's finish line, that's based on what? Kinetics, which is the rate of a reaction or speed of a reaction. So now, potentially questions like this where, okay, so temperature is low, it's not happening. Why? Because typically why? The reaction is slow at a low temperature. So you have to increase temperature value which will make what? There's a greater kinetic energy for the reactants, which will have enough energy to overcome the energy of activation, which means what? Yeah, the reaction will occur at high temperature value. So in this case, you have to mention what? Kinetics. Kinetics, okay? So the rate of a reaction depends on what? Concentration, temperature, energy of activation, catalyst, surface area, okay? So you can mention the what? Typically, you can mention what? Okay, so because due to what? The reaction perhaps have a greater energy of activation than anticipated. So because of that, the reaction rate is slow at low temperature. If temperature goes up, the particles will have enough energy to overcome the energy of activation, and the reaction rate will be appreciable. That's why you're seeing the reaction happening, a product being created. So this is more of thermodynamic perspective of the reaction versus the kinetic perspective of the reaction for part F. Let's go to part G. The question is asking, guys, okay, so this is the finding energy question, I believe. Part G, the question is asking, a partial photoelectron spectrum of the pure silicon is shown below. The one spectrum shown in the missing peak corresponds to 3p sublevel. Okay, so the question is asking in G, probably you would have to draw the missing peak, right? So if you look at this, so here you see a peak that looks like this. I mean, this is a higher value, so don't be confused with this one. The higher value, this is the lower value in terms of the energy perspective, okay? And this represents the number of electrons, relative number of electrons here. So basically the first peak with the higher value is what? This is a 1s peak, right? And then you have a 2s peak here, and you have a little bit larger peak like this. That's a 2p. So again, the height represents the relative number of electrons, okay? Because you have 2 electrons here, 2 electrons here, you have 6 electrons here, that's why the peak is higher, okay? And then you have 3s, and then you have 3p's. But based on what we put the answer for, I believe, for 2a, okay, there's what? We put the answer as any 3s2, 3p2. That's the electron configuration. So now, you have 2 electrons here, and also what? There is a p, but it has those 2 electrons in there. So you have to have a same height as 3s and have what, right? 3p there. And that will be the drawing that you have to put for part G. And part H, the question is asking, using the principle of atomic structure, explain why the first ionization energy of Ge is lower than of silicon. So if you got to go to the periodic table, see where the G is at. G is right underneath silicon. So because Ge, the definition, right? You gotta understand the first of all definition of the first energy of ionization. So the energy of ionization definition is amount of energy required to remove a valence electron of an atom at a gaseous state. So this is what it is. So it's element X at a gaseous state turns into X plus gas plus electron, okay? That's a reaction. So you're trying to pull the electron out from the atom. The electron is attracted to the nucleus, and which means you're trying to pull that out. So that's an endothermic process. The energy must be required to put in, right? So energy is required to put in. Okay, so you're putting in energy to get the electron out, right, from an atom. So, and this energy must be what we call the energy of ionization. So, and then it must be a gaseous state, as you know, but the question is asking, typically, right, when silicon is here, the next one is right there, G is right here. Why does it take less energy to remove Ge electron versus a silicon electron? So typically, questions like this, you might want to bring up the term, something called Coulombic attraction. Coulombic attraction. Okay, so Coulombic attraction is what? Attraction between a plus charge and a minus charge. Okay, so you have to sort of mention that the valence electron for Ge is coming from 4p versus what? 3p from silicon. So the outermost electron for Ge is what? Is further away compared to a silicon. It's at an outer shell compared to a silicon third principal energy level. So being of electron being further away, it has a weaker Coulombic attraction to the nucleus. Hence, it'll be easier to remove them. And what? That results in having a lower energy of ionization. So electron being further away because it's the next shell to the fourth principal energy level, it's further away, weaker Coulombic attraction. If the Coulombic attraction is weaker, it's easier to remove them, which means what? Having a lower energy of ionization. That's something they have to mention in the part H of number 2. Part I, the single photon with the wavelength provided 4 times 10 to the power of 7 meters is absorbed by the silicon sample. Calculate the energy of the photon in joules. So I think relatively simple question for I. So the equation is the energy of the photon is equal to Planck's constant times the frequency. Planck's constant is it's a constant value, Planck's constant, right? And you have to get the frequency. Okay, so they provide you with the wavelength. As you know, speed of light is equal to wavelength times frequency. That's the equation, right? So they provide you with the wavelength. You just have to plug it in there. So, and I have to get the frequency. So frequency is equal to speed of light divided by lambda, okay, which is equal to, so speed of light, I mean, you know, how I know it is 3 times the power of 8. But now I think, you know, if you go to the table in the front, if they tell you these constant values for speed of light. And if I'm not mistaken, they probably have given you as like 2.99 times 10 to the power of 8. So it's up to you guys which one you guys want to utilize, but I just used 3 times 10 to the power of 8 meters per second divided by the wavelength, which they provided as, the question, 4 times 10 to the power of -7 meters. So that'll be the frequency, okay? So the frequency, you have to put it there. So energy is equal to Planck's constant, which is equal to 6.63 times 10 to the power of -34 times the value that we got there. So 3 times 10 to the power of 8 divided by 4 times 10 to the power of -7. So the value should be, what I got is 4.97 times 10 to the power of -19 joules is the answer that I got for part I. So that will be the end of number 2.